Hello everybody, today we're going to be taking a look at this problem. The problem is pretty simple. We just need to detect a cycle in an undirected graph. So we have a graph that looks something like this. We have 0, 1, 2. This is what's known as an adjacency list. This is one of the ways of representing a graph in a dictionary format in Python, where we have each node and a node and every single node that it is connected to. So the node 0 is connected to 1 and 2, the node 1 is connected to 0 and 2, 2 is connected to 0, 1, 3, and 3 is connected to 2. So obviously I recommend if you have like a pen and paper to like draw this out. Usually I would draw this out on my iPad, but it's having some issues today, so we're just going to kind of go through it and kind of imagine what the graph would look like. But in this case, when we're trying to detect a cycle of the graph, you can imagine the word cycle. What essentially it means is you're starting at a certain node and you go through some process to get to the original node. So to find a cycle in the graph, we start at node 0 and we see that 0 goes back to 1. 1 does go back to 0, but that only counts as two nodes going back and forth. So that doesn't exactly count as a cycle. However, when we see that 0, 1, and then 2, 2 actually goes back to 0. So 0, 1, 2 goes back all the way back up to 0. So that makes sense. Now that is going to be the cycle. The cycle is going to be 0, 1, 2 in this graph. So the output of the final result we want to get is the result true. So how are we going to do this? Well, if you noticed, what we're essentially doing is we are going to be doing a sort of depth first search approach while doing this. So we have a node that we're starting with, and we're continuously going in the deepest node possible. So notice how we immediately try to go from 0, and then we check 1 first. We don't go to 2, we check 1 first, and then starting from 1, we check each individual node, obviously, and if we see that a node that's already been visited in the past, we want to return it. Obviously, we can't just have it be from 2, so we have to consider it visited. So we're going to keep a track of a variable called we're going to keep track of all the nodes that we visited in a set, and if we ever see the node in the set, like right now we see the number 2, then we can immediately say, okay, there is a cycle in this list and this graph, and we return true. So that is essentially basically the entire way we're going to be doing this. Obviously there's going to be some nuance on how we're going to be detecting the cycle, but the core approach is going to be using a depth first search to go through each individual neighbor and then continuously look to see if the parent that we originally tracked in our visited set is reached, and if it does, we can return out true, otherwise we will return false. So sounds simple enough. Let's get started. So we're going to be defining a list called, let's say, has cycle. Sorry, my double space. And then the input we're going to be taking is the entire graph. So we're just going to be passing this entire graph as this adjacency list that we're going to be putting up. Right now, to start off with, like I mentioned, we're going to be having a visited list. We're actually going to be keeping it as a set because it's more convenient to keep it as a set. It takes up less data space, and it is more convenient to just index into directly to figure out which position that we're in. Okay, so now we're going to make our DFS function, our depth first search function, and what it consists with is the node and the parent, because that's what essentially we're tracking. We're tracking the node that we're traveling within and the parent. So pretty simple to start off with. We're going to be, once we see a node, like the root node, like if we, for example, we start off with the 0, we're going to be adding the node. Now, for each node, what are we doing exactly? We are going to be running a depth first search, essentially, recursively, in each neighbor in the depth first search. So what we're going to say is for neighbor in, we're going to be looping through each node of the graph of the node. So we're going to be graph of node. This is each individual key. The node is going to be the key, and each of the neighbors we're looping through. If the neighbor is not invisited, so what does it mean when the neighbor is not invisited? It means obviously if it is invisited, we have the chance to see it's true, but let's say that it's not in the visited set that we previously seen. Like for example 0, we see 1 and 2. If it's not invisited, we're going to do another depth first search on that. So this is where we go into the depth first search recursively, where immediately we see, since this 1 is not in the visited list that we previously does, we're going to say if DFS of neighbor and node. So we're going to be calling this recursively. So where we're doing a recursive function where this node becomes the new parent of the depth first search. And we're going to be returning true. Why are we going to be returning true? Because essentially we know that there is a possibility for the node to basically be visited. So we're going to be returning true. Else if, also we need to make sure that the neighbor is not equivalent to the parent. The other condition for when we'd be returning true is once if the depth first search that we get to eventually returns true. Otherwise, if the neighbor is not equal to the parent, we're going to be returning true, because then we want to continuously go through the function. Like even if like for example we'd run this 1 on it and then continuously check to see, and eventually we'll find a neighbor that's not equivalent to the parent, and then we're going to be returning true. And towards the end of this, after all of this, we're going to be returning false. So there's two possibilities when we run through the cycle. If the cycle doesn't go anywhere and then it just continuously, like for example in the path of 0, 2, and then let's say it was 3, and then no, actually if it was just like 0, 2, 1, well that's also a cycle. But in a case where there isn't a cycle, that's when we'd see that we just return false because it doesn't go anywhere and the graph is basically done there. So now that's basically filling out this visited list where we're continuously adding nodes to the visited list using the depth first search. And now once we know what nodes that we visit in our depth first search traversal, all we need to do is loop through the graph for node in graph. We're looping through the graph that we passed through here. If the node is not invisited, so we need to check the nodes that are not visited. Like for example, we could see a cycle and that would be return true. But if we see that a node is not visited, we're going to try to see if DFS, we're going to be running a depth first search of -1. And what -1 is basically is -1 is checking to see if the parent is and a -1 value in the graph. If we see that, then we're going to be returning true. This is the example where we do see a cycle where we obviously there's a possibility that it returns true here in the depth first search that we call here for each. This is basically running our depth first search in every single graph, basically, is what I'm trying to say. And -1 represents the first the previous node, basically. If the previous node is equal, we eventually reach that, we're going to be returning true. Otherwise, we're going to be returning false. So my explanation towards the end there was a little bit messy, but essentially all we're doing is we're running this depth first search continuously on the node and the parent starts out as -1, which means the parent, and if we see that it returns true, that means we found a cycle via this depth first search function that we've seen here. So we'll return true and it'll immediately detect, yes, there is a cycle in this list. Otherwise, we're going to be returning false, essentially. So hopefully most of the logic was kind of clear there. We can just test this out by seeing the result and print of has cycle of graph undirected. We're going to see this. Let's run the code, and if we did everything right, it should detect the 0, 1, 2 cycle here, and it should return true, and it does indeed return true. So we could test this with other input cases, and I might do that in the future. The time and space complexity is both n, because in the worst case situation, we'd be going through every single node in the graph, and that would be a time space complexity of basically n, because in recursive method it's also going to be remember, we're continuously adding each and every node to the stack, so the stack could potentially be n big. And obviously we'd potentially be looping through the entirety of the list. Technically it's going to be 2n because there's a secondary loop here, but it is considered an n time complexity solution and an n space time complexity solution as well. So hopefully you guys understood the way that I explained the logic there. Hopefully my logic, especially in this last part, was a little bit confusing. But yeah, that's basically how to go through this problem, and I'll see you guys in the next video. See ya.